Less than a minute ago, scientists confirmed Mount Etna has shifted. Again, new data reveals a vast magma highway pushing the volcano's southeastern flank almost 2 centimeters closer to the sea, building unstoppable underground pressure. In 1669, a similar shift triggered disaster with little warning. Now every instrument is spiking. What's forcing Etna to move this time? And how close are we to an eruption no one can predict? Deep beneath Mount Etna, scientists have mapped a network unlike anything previously seen under a European volcano. Using seismic tomography, a technique similar to taking an X-ray of the Earth's crust, researchers at Italy's National Institute of Geophysics and Volcanology have revealed a branching corridor of molten rock stretching from 6 to 12 kilometers below the surface. This is the so-called magma highway, a term now echoed in both academic journals and late-night emergency briefings. Instead of a single pipe feeding the summit, the images show a tangled web of magma-filled channels, some running laterally for miles before curving upward or splitting off toward the flanks. The breakthrough came in May 2024, when a cluster of junior geophysicists in the INGV control room noticed subtle delays in earthquake waves arriving from small tremors beneath Zaffarana. These delays hinted at pockets of liquid rock slowing the seismic energy. Within hours, the team's tomography models rendered a three-dimensional map, thick, low-velocity zones radiating southeast from Etna's core, linking deep magma reservoirs to weak points under the volcano's moving flank. Messages fired through internal channels. Flank velocity anomaly. Possible new corridor active southward. Confirm with Sentinel. The urgency was clear. By dawn, a classified memo summarized the discovery for regional authorities. A new magma pathway was active, running directly beneath the most unstable sector of the mountain. This magma highway is not static. Over the last year, its branches have thickened and extended, connecting old reservoirs with new fractures near the Ionian coast. The main trunk sits roughly 8 kilometers down, but side branches are now traced as shallow as 6 kilometers below the surface. The network's reach is confirmed by the alignment of earthquake swarms, thermal anomalies, and rising gas emissions, each a symptom of molten rock forcing its way through the crust. What makes this discovery so unsettling is the pattern. Instead of magma rising vertically, pressure is being redistributed sideways, feeding into the flanks rather than only toward the summit. The southern and southeastern corridors, in particular, run beneath towns and farmland that have not seen major eruptions in centuries. Ground deformation maps, updated weekly, show the land above these corridors slowly bulging and creeping toward the sea. The mountain's interior, once thought to be a simple vertical stack of reservoirs, now appears as a living, shifting latticework, one that is actively reshaping the surface above. For the first time, scientists can visualize how Etna's deep plumbing connects to the dangerous sliding of its southeastern flank. The magma highway is not just a scientific curiosity. It is the hidden engine driving the volcano's movement, a force that is both expanding and unpredictable, pressing against the boundaries of what the mountain and the people living on its slopes can withstand. Sentinel-1 satellites, orbiting hundreds of kilometers above Sicily, have tracked a subtle but relentless movement on Mount Etna's southeastern flank. Using radar interferometry, known as INSAR, these satellites can measure ground shifts as small as 2 millimeters per year. The data is unequivocal. The entire southeastern sector of the volcano is inching toward the Ionian Sea at a steady rate of about 2 centimeters each year. This pace may sound slow, but in the world of geology, it is rapid, especially for a mountain that towers over populated foothills and coastal towns. The precision of these satellite measurements is remarkable. By comparing radar images taken days, weeks, and months apart, scientists construct detailed maps of ground deformation. The results reveal a broad zone, stretching from the summit slopes down through Zaffarana and toward the coast, that is sliding outward as a single, massive block. The movement is not uniform. Some areas creep faster, others lag behind. But the overall drift is clear and persistent. GPS stations anchored deep into the rock confirm the figures, matching the satellite's readings to within a margin of 2 millimeters per year. This agreement between space-based and ground-based instruments leaves little room for doubt. Over the past decade, cumulative ground displacement in some neighborhoods has reached nearly 20 centimeters. Local residents may not notice the shift in their daily routines, but property surveyors and civil engineers have documented cracks in roads, misaligned door frames, and subtle tilts in buildings, physical evidence of the mountain's slow march toward the sea. For the people living on these slopes, such changes are a reminder that the ground beneath their feet is anything but stable. What drives this movement is a combination of gravity and the underlying geology. Etna's southeastern flank sits atop layers of ancient marine sediment that dip toward the coast, creating a natural slide. The immense weight of the volcanic pile, pressing down on these weak layers, sets the entire sector in motion. While magma intrusions can accelerate the process during eruptive episodes, the background rate of 2 centimeters per year persists even in quiet periods, a silent, ongoing adjustment of the landscape. The implications extend beyond slow deformation. Scientists warn that steady creep can weaken the structure of the volcano over time, priming it for sudden slips or even catastrophic collapse if triggered by an earthquake or a surge of magma. The 2016 to 2017 seafloor geodetic campaign showed that this movement doesn't stop at the shoreline. Acoustic sensors on the seafloor detected a matching slip event offshore, confirming that the mountain's instability continues beneath the waves. Each new dataset adds to the growing consensus. Etna's southeastern flank is not just restless, it is actively shifting, and the precision of today's measurements leaves no room for comfortable denial. This ongoing motion is not a distant geological curiosity. It is a process unfolding in real time, directly affecting the safety of tens of thousands who live and work on these slopes. The mountain's slow creep, measured with millimeter accuracy from space, is a warning, written into the land itself. A sign that the forces shaping Etna's future are already at work. At 2:14 in the morning, the INGV control room in Catania was anything but calm. Log entries show a flurry of messages. Flank velocity anomaly. Possible new corridor active southward. Confirm with Sentinel. Junior analysts huddled over monitors comparing real-time seismic feeds with satellite overlays, while senior volcanologist Marco Neri scrolled through a growing list of flagged alerts. The language in the logs was clinical, but the tone had changed. By 8:22 a.m., a formal memo was drafted and marked for immediate delivery. Initiate weekly enhanced monitoring protocol for southeastern sector. Alert issued to Civil Protection Unit. Await confirmation by satellite cross-checks. The word unprecedented appeared twice in the summary, a term rarely used in routine reports. Internal emails, identical in English and Italian, were labeled for review, classified, do not disseminate beyond operational team. The memo to regional authorities, sent within 24 hours, laid out the findings with uncharacteristic bluntness. A new magma pathway was active, running directly beneath the most unstable part of the mountain. One line, quoted later in press briefings, captured the mood. "It's like the volcano is stretching." The INGV staff, usually measured in their public statements, began fielding calls from civil protection agencies and local mayors. The control room's Slack channel filled with urgent requests for updated hazard maps and projections. In a recorded exchange, satellite deformation analyst Paola Pingue admitted, "Every instrument points to instability, but the system's complexity exceeds prediction capacity." By midday, the monitoring protocol had shifted from standard daily summaries to round-the-clock watch, with teams assigned to cross-check every spike in seismicity, gas output, and ground deformation. The routine of measured observation had given way to a sense of active vigilance. The language in the logs, pulse through the crust, corridor expansion, instability increasing, reflected a new reality. The volcano's deep machinery was no longer behaving according to established patterns. For the first time in years, the scientists themselves sounded alarmed. Lateral magma intrusion is a process that turns the heart of a volcano into a dynamic, shifting engine of instability. On Mount Etna, this means molten rock is no longer content to rise straight upward toward the summit. Instead, it pushes sideways, threading through fractures beneath the flanks and forcing the mountain's outer shell to stretch and deform. Field volcanologists like Marco Neri compare this to prying open a crack in a dam. The pressure doesn't just lift, it wedges apart, exploiting every weakness in the structure. Recent seismic and satellite data show that these sideways intrusions are feeding directly into the southeastern sector, where the mountain is already sliding toward the Ionian Sea. The magma acts like a hydraulic ram, prying open faults and lubricating the deep slip surfaces that separate the volcanic pile from the older marine sediments below. As magma forces its way into these corridors, it redistributes stress along the base of the mountain, weakening the natural friction that holds the flank in place. The result is a system where gravity and magma work together, each amplifying the other's effect. This mechanism is not just theoretical. During episodes of rapid intrusion, GPS stations and ground radar have tracked sudden surges in surface movement, sometimes several centimeters in days, coinciding with bursts of seismicity and gas emissions. These events are short-lived but significant. They can trigger shallow faulting, open new fissures, and accelerate the long-term creep that is already measured at 2 centimeters per year. The danger lies in the cumulative effect. Every pulse of lateral magma, every slip event, brings the southeastern flank closer to a threshold, where friction gives way to collapse. Volcanologists in the field walk these fissures, measuring offsets and mapping fresh cracks that zigzag through orchards and farmland. Their data feeds into mechanical models that simulate what would happen if a major slip occurred. The consensus is sobering. If enough pressure builds and the deep faults unlock, a sector of the mountain could fail catastrophically, sending millions of tons of rock toward the sea. It is this interplay of magma intrusion, structural weakness, and relentless gravity that keeps scientists on constant alert, knowing that the mountain's next move may come without warning. In the spring of 1669, Mount Etna's southern flank ruptured in a way that still haunts Sicilian memory. The first cracks opened not at the summit, but miles downslope, long, jagged fissures tearing through farmland and vineyards near Nicolosi and Mascalucia. Within hours, molten rock surged from these wounds, pouring downhill with a force the region had never witnessed. Parish records and merchants' logs from that year describe midnight evacuations, families fleeing with only what they could carry, and livestock driven ahead of advancing fire. Entire villages vanished beneath the lava, including Malpaso and Mister Bianco. The flow did not stop for weeks, carving a blackened path all the way to the city walls of Catania. Parts of the city itself were buried, and the coastline was pushed outward by the cooling mass. Contemporary engravings and maps show the devastation in stark detail. Modern overlays reveal that some of today's bustling neighborhoods and fertile orchards sit directly atop the ancient 1669 flow. The eruption provided almost no warning. There were no coordinated evacuations, no scientific forecasts, only a sudden outbreak of fire and the relentless advance of lava. The destruction was not contained to the summit or upper slopes. It struck where people lived and worked, far from the main crater. The historical record makes clear that Etna's most devastating events can begin with little notice, miles away from the volcano's peak. The southern fissures of 1669 were fed by underground channels, hidden corridors that allowed pressure to escape laterally, bypassing the summit entirely. This pattern, mapped in old letters and parish accounts, is now confirmed by modern science overlaying flow paths from centuries ago, with the subsurface magma highways seen today. The lesson of 1669 is not just a story of past loss. It is a reminder that when Etna's deep mechanisms shift, the consequences can unfold far from where anyone expects, with devastating speed and reach. 4 independent alarms now pulse through Mount Etna's monitoring network. First, a swarm of low-frequency microquakes, some barely strong enough to rattle glass, registers deep under the southeastern flank. These tremors, clustered at depths of 6 to 10 kilometers, trace the path of magma forcing its way through solid rock, widening fractures as it moves. At the same time, gas monitors on the lower slopes detect a sharp spike in sulfur dioxide and carbon dioxide, with levels in September 2024 reaching their highest point in nearly a decade. Helium isotope ratios, sampled from peripheral vents, show signatures that match magma rising closer to the surface. Infrared satellites add a third warning. Faint but persistent thermal hotspots now dot the base of the volcano, appearing and fading in a slow, rhythmic pattern. This pulsing heat, described by INGV scientists as "the mountain is breathing again," matches the tempo of gas surges and microquake clusters. Finally, deep gas isotope analyses confirm that these emissions are not just surface leaks, they originate from the same deep reservoirs feeding the newly mapped magma highway. Each signal alone might be dismissed as routine. Together they spell active unrest, converging on a system that is anything but quiet. Mount Etna's underground network does not stop at the mountain's base. Recent anisotropic seismic imaging reveals that the magma highway extends far beyond Etna, tracing a path toward the southern Apennine belt. This wider system links deep magma reservoirs under Sicily to tectonic fault lines that stretch across the Mediterranean. The volcano's restless activity is not just a local phenomenon. It is part of a much larger geodynamic engine, shaped by the ongoing collision between the African and Eurasian plates. As the African plate dives beneath southern Europe, intense compression builds up beneath Sicily, creating the heat and pressure that feed Etna's magma supply. This subduction zone is among the most active in Europe, generating earthquakes and fueling volcanoes from the Tyrrhenian coast to the Ionian Sea. The magma highway, mapped by directional wave analysis, shows a clear preference for southeastward flow, following the same structural weaknesses that have guided eruptions for thousands of years. Scientists now see Etna as a single node in a vast, interconnected network of volcanic and tectonic forces, one that can transmit stress and magma across regions, raising the stakes for all of southern Italy. On the southern slope, the DeMarco family tends to their vineyards and lemon groves as they have for 3 generations. Their home in Zafferana sits just above the ancient path of the 1669 lava flow, a reminder that the land's bounty comes with risk. Salvatore DeMarco, now in his 70s, keeps an evacuation kit by the door. He remembers the 1983 and 1992 eruptions, when the family left in the middle of the night and returned to find fields changed by new rock. His grandchildren study geology at the university in Catania, hoping science will give them more warning than their ancestors ever had. Towns like Zafferana, Nicolosi, and Padara together hold over 30,000 people who rely on the fertile soil for their livelihoods. Civil protection plans exist, but some evacuation maps are based on hazard models that remain partially classified, and not all local officials have access to the latest tsunami scenarios. Gaps in monitoring, like the 3-week sensor outage during heavy ashfall in 2022, have left residents uneasy, aware that even the best technology cannot guarantee perfect warning. For families on Etna's slopes, life is a balance between tradition and the knowledge that the volcano's next move could come without notice. Satellite data confirms Mount Etna's southeastern flank is moving toward the Ionian Sea at a rate of about 2 centimeters per year, a shift matched by evidence from seismic tomography revealing an expanding magma highway 6 to 12 kilometers below the surface. These findings, supported by the Italian National Institute of Geophysics and Volcanology, show the volcano's internal structure is changing in ways not seen before. The same southern flank that erupted with little warning in 1669 now shows rising gas emissions, ground inflation, and synchronized microquakes. While scientists have mapped the magma's new path and documented 4 independent warning signals, they cannot yet predict when or where the next eruption might occur. Tens of thousands in towns like Zaffarana and Nicolosi remain in the zone of uncertainty. The classified tsunami models and withheld collapse scenarios underscore the risk. For now, every instrument points to a single fact: Etna is more dynamic and unpredictable than ever recorded. The mountain's next move remains unwritten.